All right, thank you very much, and thank you everyone for being here today. So in this seminar, I'll be presenting the work that I've been undertaking in the last 3.5 years towards my thesis, and that's titled Heuristic-Based Self-Assessment of Target Localization During Robot-Assisted Shoulder Surgery. This work that I'm presenting today has been supported by the QUT Center of Robotics and the ARC ITDC for Joint Biomechanics. This has already been mentioned, but I'd like to acknowledge the Turrbal and Yagara people as the First Nations owners of the land where QUT now stands, and pay my respects to their elders, laws, customs, and creation spirits, and recognize that these lands have always been places of teaching, research, and learning. I'd also like to warn you that there are a few images and some descriptions of surgery in this seminar, just in case that's something that will make you uncomfortable. So, localization is everywhere. Localization is the ability to determine where something is, and it's used by all of us in our day-to-day lives, and it's something that's really important to robotics. There's multiple types of localization. We have ego localization, which is the ability of a robot to find its location in the world. And this is really critical to being able to navigate from one place to another. And this is the sort of localization that's necessary for mobile robots, autonomous vehicles, and UAVs. Another type of localization is target localization. And this is the ability of a robot to find where something is in the world relative to itself. And this is necessary for interacting with the world. So this is something that robot manipulators need to find an object to be able to pick it up. And it's also the type of localization that's necessary for surgical robots, which is what we're interested in today and in this thesis. Localization is a fundamental ability for robots to be able to function autonomously in the world. But as well as being important, localization is quite difficult. There are a range of different challenges in different types of localization. For visual localization, for instance, which is the type that we're particularly interested in this thesis, and that's localization using cameras, we have challenges like viewpoint and illumination changes, which will make the same object or the same place look really different under different conditions. We have problems with occlusion and aliasing. And this isn't unique to just visual localization. Other localization types, for instance, GPS-based localization can have problems with multiple path errors, and IMU localization can accumulate drift over time. What this means is that the ability of a robot to self-assess its own localization estimate, determine if that's accurate enough for the task it's trying to achieve, is really critical to it being able to operate autonomously. This means that self-assessment is necessary for localization to be able to operate effectively and safely in real deployments. And this is particularly important in safety-critical applications like surgical robots, where error tolerances are very low, normally measured as a few millimeters or a few degrees, and the consequences of mistakes are potentially catastrophic. In this thesis, our objective is to establish a foundation for visual localization in robot-assisted total shoulder arthroplasty, which is a surgery I'll talk about in a minute. To establish this, though, we have two key investigations that we undertake. The first is exploring how we can detect instances of localization failure, and the second is how we can use these detections as an opportunity to try and improve localization accuracy. In the rest of this seminar, I'll go through a literature review providing an overview of some of the background topics necessary for this thesis. I'll then go through the three contributions in the thesis. Our first, exploring localization failure detection and leveraging those to improve localization performance. Our second contribution, where we look at predicting localization failures ahead of time before they occur. And in our third contribution, where we refocus again on improving localization accuracy, this time using self-assessment to inform the way the localization pipeline works itself. I'll then provide a summary of the contributions and some future directions of research that I'm interested in. And that brings us to our literature review. So here in the literature review, I'll introduce total shoulder arthroplasty surgery, computer-assisted orthopedic surgery, and an introduction for localization integrity and self-assessment. In this thesis, we're particularly interested in one type of surgical procedure, and that is the total shoulder arthroplasty. This is an orthopedic surgical procedure that replaces the glenohumeral joint in the shoulder. This is the main joint in your shoulder where your humerus, or your upper arm bone, articulates on a shallow socket called the glenoid, and that's part of your shoulder blade or your scapula. This is the fastest growing joint replacement procedure in the world. In the last 14 years here in Australia, we've seen about a 230% increase in the number of annual cases. Generally speaking, patient outcomes following total shoulder arthroplasty are pretty good, but there are still some problems. At the moment, we have about an 8% revision rate. What that means is that in Australia, 8% of all of these surgeries that are performed are a second or subsequent procedure because of a complication, because something didn't quite go right in the previous surgery. The two most common causes for complications are glenoid implant loosening and wear and joint instability. And both of these complications are linked to glenoid implant positioning errors. This is particularly critical when we consider that there's a growing body of evidence showing that traditional manual instrument techniques for placing these implants are inaccurate. Some studies report nearly 70% of glenoid implants placed using manual instruments meet the clinical definition of malpositioning, which is more than 4 millimeters or 10 degrees deviated from the planned position. So this is very significant. So glenoid positioning during this surgery is challenging. During this procedure, the final position and orientation of this implant is defined by the surgeon when they place a guide wire into the glenoid bone, which is what we can see here in this top image. The tools that then prepare the bone for the implant slide over the top of this guide wire or are placed with reference to it, which is what we can see here. This is a hollow reamer that slides over the top of the guide wire. This means that getting the glenoid guide wire in the right place is critical to implant positioning. If we can improve the accuracy of this, we can improve the accuracy of the implants, and we can potentially reduce complication rates. And this is something that robots have the potential to help us with to improve patient outcomes. So this idea of using computer-based systems to help surgeons plan and execute orthopedic surgeries is not new. It's been around for a number of decades now. And the catch-all term for these systems is computer-assisted orthopedic surgery. There's a few different types of these systems. We have patient-specific instruments, which are custom manufactured tool guides that clip onto a bone in one specific way. We have surgical navigation systems. These provide real-time visual feedback to the surgical team on the positions of tools and the patient relative to the preoperative surgical plan. And then we have surgical robots, which is what we're particularly interested in because robots are cool. Surgical robots for joint replacement procedures, they help guide the cutting tools that the surgeons use to prepare bone during those bone preparation steps of the surgery. And the use of these robots has been shown to improve implant positioning accuracy in hip and knee procedures, but we don't have any data available for shoulders at the moment. The first robot approved for use in shoulder arthroplasty was only announced earlier this year, so it's still brand new. In order for these robots to function, they need constant knowledge of where the patient's bones are and where the surgical tools are. And this is a localization problem. The tissue that we're interested in is rigid bone, and that means that our localization problem is fundamentally a rigid object 6 degree of freedom pose estimation problem. Current commercial orthopedic robots solve this issue using optical tracking. Many of you in the room will be familiar with Vicon or OptiTrack systems that track reflective markers in space, and this is essentially the same technology. So these systems are really accurate, but they do have a few drawbacks. One of the big ones is that everything that's tracked has to have a marker attached to it, and that includes the patients. So you can see here markers that have been screwed down into patients' bones in order to be able to track those. And this has some challenges associated with it and can potentially introduce new complications. Visual localization systems, on the other hand, have the potential to remove the need for marker-based tracking. But the visual localization conditions in surgery are extremely challenging. There's really harsh lighting on reflective surfaces. There's sparse textures on bones, and there's a lot of occlusion of the object. What this means is that for visual localization to be feasible in guiding surgical robots, we need to develop self-assessment systems so that we know when the localization results we're getting are accurate enough for the job we're trying to do. And that brings us to localization integrity and self-assessment. Localization integrity is the level of trust that we can place in a localization estimate being within an acceptable tolerance of ground truth. It's the ability of a localization system to self-assess its own performance and make a decision as to whether or not it's acceptable or not. And this isn't by any means a new concept. In life-critical fields like aviation, localization using GPS has had integrity measures attached to it for decades. But this is still a relatively new idea in robotics. Over the last few years, we've seen an increase in interest in autonomous vehicles. And a lot of the localization integrity research we've seen in robotics has focused on autonomous vehicle applications, meaning it's also focused on localization using sensors that are relevant to autonomous vehicles. So GPS again, and LiDAR-based localization. Despite significant advances in visual localization systems, we've seen very little research in localization integrity for visual localization. One area of visual localization we have seen recent research for localization integrity is visual place recognition. This is a localization approach that frames the problem as an image retrieval problem, where an image captured by a mobile robot is compared against a database of known places in order to identify where the robot is. Methods for self-assessment in visual place recognition have broadly used one of two approaches. They've either used binary classification, where the result of a VPR query is either labeled as within tolerance or outside of tolerance, or they've built probabilistic models that return a percentage chance of the result being within tolerance. Something that's really exciting, though, in the papers looking at self-assessment for VPR is that these approaches, using both different methods, have been shown to improve the accuracy of downstream localization tasks. So this means that in addition to helping to improve safety, self-assessment can be used to help us improve our localization estimates in the first place. So self-assessment has also been explored for 6 degree of freedom pose estimation, and that's that fundamental problem that we have here in localizing patient bones. Usually in the literature, this is termed uncertainty quantification. And broadly speaking, most of the research has aimed at pulling a confidence score for a pose estimate out of a deep learned layer within a complex 6 degree of freedom pose estimation system. So this has been done by pulling confidence scores out of object detectors or semantic segmentation stages, but these approaches provide no information on the quality of the resulting pose estimate. Other approaches have actually trained deep neural networks to output a confidence of the pose that they produce, but these have been shown to poorly correlate with the actual errors that the poses have. We've also seen other methods using ensemble approaches where multiple 6 degree of freedom pose estimation systems are deployed in parallel, and then the agreement or disagreement of the resulting poses is used to get a measure of the confidence of the results. We've also seen the use of uncertainty from deep learned key point feature detectors, where these individual key point uncertainties have been used to either weight points or weight correspondences in the pose recovery algorithm, or in one particularly interesting work has been applied with some statistical machinery to give a statistically guaranteed worst case error. And this is particularly exciting as this quantifies error rather than giving a specific rather than giving a confidence score. So while self-assessment has been explored for visual localization and 6 degree of freedom pose estimation, no one has done any exploration of this within the context of visual localization for guiding surgical robots. And that's what we're interested in. So in summary, surgical robots have the potential to improve patient outcomes by improving implant positioning. Localization self-assessment is necessary for visual localization to be feasible in guiding these robots in this task. It hasn't been explored in this context of surgical robots, and we also have potential to improve our localization using this self-assessment. And that brings us to our first contribution here in the thesis. So in our first contribution, we investigate both detecting localization failures and leveraging these detections to improve localization performance. And the work presented in this contribution has been published in the IEEE International Conference on Robotics and Automation in 2023. So in this first contribution, we consider two separate aspects to localization self-assessment. The first being that individual target pose estimates may have unacceptable errors. And second, that localization accuracy may vary between different target viewpoints. And so to address both of these, we propose a two-stage process to localization self-assessment. In our first stage, we classify individual target pose estimates as either accurate or inaccurate, so within our error tolerance or not, treating this as a binary classification problem. And then we build on this to characterize localization performance at a specific camera viewpoint by building a consensus of individual target pose estimates. So in the approach that we propose, we build on top of a 6 degree of freedom pose estimation pipeline that localizes a target object with respect to our robot. For every pose estimate that is generated by this pipeline, we extract performance heuristics from within the pipeline, and we use those as input features for a binary classifier model. And that binary classifier model then labels each of our target pose estimates as accurate or inaccurate. Once we're able to label each of our target pose estimates, we can then characterize localization performance for a particular camera viewpoint by taking multiple target pose estimates, predicting whether they are accurate or inaccurate, and scoring our localization by calculating the ratio of pose estimates that are predicted to be accurate. In terms of specific implementation, the 6 degree of freedom pose estimation system we use in this is a PNP ransack pose estimation system built on top of a key point feature detector. And the performance heuristics that we pull out of this pipeline are the number of key point features used for the pose estimate, their spatial distribution across our target object, and the reprojection error of the resulting pose estimate. The binary classifier model that we use to make the predictions of accurate or inaccurate is a support vector machine that's pre-trained. Now that we have two different ways of measuring localization accuracy, we have two proposed methods to improve the localization performance. The first is through pose estimate filtering. To apply this, we just take any individual pose estimate which is predicted to be inaccurate and we reject it, not passing it on to any downstream tasks. Our second approach uses the characterization of localization performance from a specific viewpoint, and it uses this information to inform robot trajectories. Specifically, we propose a sample and predict approach. In this, we have our robot move through and sample multiple potential target approach trajectories at their starting points. We then apply our self-assessment process to predict localization performance at each of these starting points and rank them. The robot then repositions itself at the highest ranked starting point and begins to approach the target. While it's traversing towards the target, it stops to reevaluate localization performance regularly. And if at any location along this trajectory, it predicts the localization performance will drop below a specified threshold, it then reevaluates the localization performance at alternate approach trajectories. If it finds one that's suitable, it repositions to that trajectory and continues approaching. And if it exhausts its search space, it predicts a complete localization failure and indicates to the user that it's lost and needs help. To evaluate this approach, we conduct a series of offline dataset experiments and live robot trials. In all of these experiments, we set our error threshold, which defines unacceptable pose estimate accuracy or unacceptable localization, to 4 millimeters and 10 degrees, which is the same error threshold that defines a malpositioned implant in total shoulder arthroplasty. For our localization targets, we use photographs of a human glenoid during total shoulder arthroplasty, so surgical specific localization targets. The 5 data sets that we collect are the robot sampling its workspace above a localization target in a grid type pattern. And in our live robot trials, we implement our approach for target approach trajectory selection. Our first set of experiments evaluate our classifier model. So that's the binary classifier that predicts if individual pose estimates are accurate or inaccurate. To do this, we process each of our data sets through 4 different variations of our pose estimation system. We train our classifier on a subset of data from one of those data sets processed through one iteration of our pose estimation pipeline, and use it to predict labels for all the rest of our pose estimates in all of our data sets. We evaluate our classifier against a weighted random guesser, as we don't have a benchmark in literature that we can compare against, so we evaluate if we're at least better than a random guess. In these experiments, using precision at matched recall, we see that our classifier achieves a mean increase in precision of 32%. So it's a significant improvement in precision over a random chance, but there is still a gap between our performance and perfect performance. Our next set of experiments evaluate using our classification approach to improve performance through filtering. In these experiments, we process each of our data sets through all of our iterations of our 6 degree of freedom pose estimation system, and we compare the error before filtering and after filtering. So to apply the filtering, we predict an accurate or inaccurate label for every target pose estimate, and we remove any of the pose estimates that are predicted to be inaccurate. Despite imperfect classifier performance, this provides us with significant reductions in localization error, with an approximately 26% reduction in both translation and rotation error across our data sets, comparing pre-filtering and post-filtering. Here we can see the results of our live robot experiments. So each of these plots represents the workspace of the robot, with our localization target here at the bottom. The colored squares are the ground truth localization performance at sampled positions, with darker colors indicating higher error and lighter colors indicating lower error. And the black line that you can see is the trajectory that the robot selected using our approach. So as we can see here in trial 3, highlighted in the middle, the robot using our approach was able to correctly identify that localization performance was unacceptable on its existing trajectory, and that it needed to alter its trajectory to an alternate one, which is what we can see here with the deviation in the line. In trial 5, using our approach, the robot was able to correctly identify that localization performance was not going to be acceptable on any of the alternate approach trajectories, and so it stopped and asked for help, which is what the red dot here at the second from last stop indicates. Comparing localization accuracy across the trajectories selected by our approach and the trajectories rejected by our approach, we can see a really significant reduction in errors here, with 96% reduction in both rotation and translation errors comparing the different trajectories. Collectively, these results show that we can use performance heuristics from within a 6 degree of freedom pose estimation system to infer performance of the localization system. But importantly, these localization self-assessment methods can provide a lot of opportunity to improve performance by reducing errors. And that brings us to our second contribution. In the second contribution of this thesis, we instead look to predict localization failures ahead of time. And the work discussed in this has been published in the IEEE Robotics and Automation Letters earlier this year. So in our first contribution, we detected localization failures after they occurred. However, even if they're detected, any localization failure has the potential to result in an unsafe action for a robot. If we can predict localization failures ahead of time, we have the opportunity to change the behavior of a robot so that it never reaches that failure, or at least have the robot ready to undertake some kind of recovery action, for instance, handing off control to a surgeon. In this contribution, we extend our previous work on heuristic-based self-assessment, and this time use it to predict when localization failures are likely to occur before we actually reach that point. So, in our proposed approach, the key idea here is to model the change in performance heuristics as a robot moves during a task, and use this model to predict likely localization at places that haven't yet been explored. To do this, we have a 3-stage process consisting of data collection, heuristic model construction, and then localization performance prediction. In our first stage, as a robot moves during a task, we collect performance heuristics from our localization pipeline and information about the robot's motion. Again, we build on top of the same 6 degree of freedom pose estimation system that we used in our previous work. This time, we only use a single heuristic, which is the number of ransack inliers returned for each of our target pose estimates. So the robot collects that along with information about its own motion. In our second stage, we build a heuristic model that maps the values of that performance heuristic with changes in target viewpoint. So we frame this model in a simplified case for a specific type of trajectory using treating it as a regression problem. Specifically, we use nonlinear least squares regression to fit a curve to the trend between target viewing angle and the number of ransack inliers we see at that target viewing angle. In our third step, we predict localization failure. To do this, we use our pre-constructed model to predict the number of inliers we expect to see at target viewpoints that we haven't yet visited. And we then predict that localization performance will be unacceptable for any target viewpoint where the number of inliers is less than a critical threshold. And this is a tunable parameter that we can set. To implement this, we propose 2 different versions of our predictor. The first is a long-range predictor that uses a minimum amount of data sampled at the beginning of a task to build the heuristic model and make a single prediction as to how far the robot can move along a trajectory before reaching failure, and a next step predictor. And our next step predictor continually updates its heuristic model as the robot moves in order to update its prediction of where localization failure will occur to stop the robot just before it gets there. Again, to evaluate this approach, we conduct a series of online robot trials and offline dataset experiments. In our offline experiments, we collect 21 datasets this time of surgical and non-surgical targets. So the non-surgical targets are just textured blocks, and the surgical targets are human glenoid phantoms, one of which has been prepared for glenoid implant placement, which is what you can see here. In these experiments, each of these data sets represents a robot trajectory around the target object, and we apply our prediction approach to see how far along the trajectory in the data set the robot can move before localization failure, and we compare the actual failure point with the predicted failure point. We do this for 2 separate error thresholds, the first being the 4 millimeters and 10 degrees that we used previously, and a newer, tighter error threshold, which is 2 millimeters and 3 degrees. And that is in line with the claimed accuracy of some shoulder arthroplasty navigation systems, so some actual computer-assisted surgical technologies. We compare our approach against a naive baseline, and this naive baseline just sets a static workspace limit as to where the robot should be able to go and only lets it move up to that point. In our comparisons, we use 2 metrics, safe path length and incursion rate. Our safe path length metric measures how far along the trajectory the predictor allows the robot to move. And this measures how useful the robot is when the predictor is applied. A larger safe path length metric means more usable space for the robot. Our other metric is incursion rate. And our incursion rate metric measures how often a predictor overestimates localization performance and allows the robot to move to a point where its localization fails. In this case, a lower incursion rate means a safer robot. Either of these metrics can be optimized on their own by either massively over or underestimating the localization performance. The trick, though, is to maximize our safe path length, so our usable space, while minimizing our incursion rate, which is our errors. In our live robot experiments, we had our robot play a game of operation, for anyone who's familiar with that. So we simulated a surgical task where we had a robot-mounted guide wire placed in a pre-drilled hole on a model of a human glenoid. We then had the robot move in an arc around the model, relying on visual localization alone to maintain the tip position of the guide wire. We applied our next step predictor approach and predicted where the robot should stop in order to not reach localization failure, but we allowed it to actually continue anyway until it really reached failure, which we defined as the guide wire bumping the model or entirely removing the wire from the hole. and then we compared the two predicted and actual failure points. Here we can see results for our dataset experiments using our long-range predictor. So on our horizontal axis, we can see our mean safe path length metric, which is usable workspace. And on our vertical axis, we can see our incursion rate or our error rate. Each of these curves was generated by sweeping the operating point of our approach and our baseline comparison. We swept the baseline comparison by just adjusting how far it let the robot move. And we swept the decision threshold. So that's the number of inliers that our approach uses to decide where localization failure has happened. What we can see here is that our predictor provides a significant improvement over our naive baseline in terms of mean safe path length with zero incursion. So using our predictor, we get a mean increase of 84% in safe path length with no localization failures. Another thing to note from these results is that our approach, which is the red dotted line, achieves a consistently lower incursion rate for matched safe path length. So we have fewer errors for the same amount of robot workspace use. We see a similar set of results here for our next step predictor, again highlighted in green to make it a little easier to see the plots. This time, our next step predictor achieves a 102% increase in safe path length versus our naive baseline. And this also represents a nearly 10% improvement over our long-range predictor. This plot here shows the results for our live robot trials. So we can see the amount of trajectory that the robot was able to traverse across, with red line being predicted points of failure and the blue line being the actual points of failure. Using our approach, the robot was not allowed at any point to reach a localization failure. So that's the equivalent of a zero incursion rate, so no errors, which is good. And we also achieved nearly 75% of the actual safe workspace usage. So that's 3/4 of the way to actually reaching failure. What these results collectively show is that by modeling performance heuristics with respect to robot motion, we can predict localization failures ahead of time for specific types of trajectory. And that brings us to our third contribution. In this third contribution, we refocus again on improving localization accuracy using self-assessment processes, this time by informing changes to the underlying localization pipeline itself. So in our first contribution, we propose to improve localization accuracy by avoiding errors, by rejecting pose estimates that had high predicted errors, and by selecting approach trajectories that minimize challenge. In this work, we extend that investigation, this time looking at informing changes to the underlying pose estimation system itself. Instead of deploying a single optimal localization system, we instead propose to use self-assessment to switch between different localization system configurations based on which is predicted to be the highest performing at any time. So our core idea here is to switch between systems with different failure modes. If we have two approaches that fail at different times, if we can pick the one that isn't failing, then we have a system that works better across the board. To do this, we need to select approaches that have complementary performance, and this is something that's been used in other localization types, for instance, visual place recognition. So complementary performance here is just performance characteristics of systems that complement each other. To do this, with our approach, we establish a default localization system which works accurately, but has a tendency to fail brittly. And we have an alternate configuration. And this is a more generalist configuration, but it has slightly higher errors, but works in a wider range of conditions. Using the same 6 degree of freedom pose estimation system that we've used in our previous works, we achieve this by tuning our inlier-outlier threshold in our ransack loop. For our default configuration, we have a very low inlier-outlier threshold. This means that our ransack loop rejects a lot of correspondences, but when it has a sufficient number of correspondences to estimate pose, those pose estimates tend to be very accurate. Our alternate configuration, on the other hand, we have an increased inlier-outlier threshold. And that means that this system rejects fewer correspondences, meaning it is less likely to the catastrophic failures that we get in the first case from being unable to achieve a ransack consensus. But it's also more likely to include poor correspondences that result in a less accurate pose estimate overall. So applying this to our approach to improve localization performance, we start with our default configuration. For every incoming image frame, we process it through our default configuration. We estimate a target pose, and then we look at the number of inliers that are associated with that individual target pose estimate. For any frame where that number of inliers is less than a threshold that we use to switch, we assume that the resulting pose is inaccurate, and we reprocess the image through our alternate pipeline. To evaluate this, we use dataset experiments, again with our human glenoid targets, which you can see here, with each of our datasets representing a trajectory from an oblique viewing angle of the model through to a goal pose with respect to the target that would enable the robot to place a guide wire. We collect these datasets with two different models, the same ones that we used before, and this time we only use our 2mm and 3-degree error tolerance. In our evaluations, we use a task success rate metric and a best choice metric, where our task success rate is the number of datasets, so the number of trajectories that a localization system is able to traverse entirely through without failing. So this is how often that localization system would have let the robot place the guide wire within our error tolerance. And then our best choice metric, which is the percentage of datasets for which an individual localization system is the best option. It allows the furthest traverse before failing. So this allows us to measure the best option, even if it didn't necessarily result in task success. So we can see here a table of lots of numbers where we compare our approach to switching between two different configurations versus a whole lot of static configurations. So each of these numbers here is the performance of our localization system with a different inlier-outlier threshold. We also compare against a number of different greedy dynamic baselines. And these search through each of these individual static configurations frame by frame and pick whichever one gives the highest number of inliers to try and get whichever is going to provide the best pose estimate. What we can see here, though, is that our approach for just switching between two specifically chosen configurations based on a performance heuristic, we achieve nearly an 18% higher task success rate and nearly 22% higher best choice metric, with our approach for switching providing better performance than either of the individual approaches that it switches between. We did some experiments to evaluate the sensitivity of our approach to different parameters. On the left-hand side here, we can see experiments comparing different default and alternative configurations of our approach, so the different two underlying approaches that we switch between. And we compared these using our task success rate metric. We can see here highlighted in orange the two best performing combinations. And the way that the color here goes from dark to light very quickly shows us that this approach is quite sensitive to the choice of underlying system. But that is to be expected given that we're specifically choosing systems that fail differently, which means that if we pick two approaches that have similar or the same failure modes, we'll get very little or no performance improvement. In contrast to that, we also did an investigation on how sensitive our approach is to the decision threshold, so the point at which we decide to make that switch from our default to our alternate configurations. We've got our decision threshold along the bottom here and our task success rate metric on our vertical axis. And we can see here that the range of decision thresholds that we have our peak performance at is quite wide. And the range of decision thresholds where we outperform the underlying configurations, which are represented by these horizontal lines, is quite enormous. It's like 100 different values will provide an improvement over the baseline. So it's nowhere near as sensitive to the decision point as it is the underlying configurations. And these two plots highlight how our system is able to perform better than the two underlying approaches, and also a key limitation. Each of these plots shows the traverse through our trajectory. So each individual point here is one of our frames from the start of the trajectory to the end. And on our vertical axis, we have our rotation error with each point representing an individual pose estimate. So on the left, we can see an example of why our system is able to outperform the underlying two approaches. Our default configuration, which is the red circles here, we can see has a significant increase in pose estimate error towards the end of the trajectory, meaning that it wouldn't have allowed the robot to get to the end of the trajectory, it would have failed late. Our alternate configuration, on the other hand, has higher errors towards the middle of the trajectory, so it would have failed as well, but earlier on. Using our approach, though, as you can see here, using the default configuration early and then switching to the alternate configuration, our approach is able to maintain acceptable localization performance throughout the whole trajectory traverse, even though both of the individual systems would have failed. In the right-hand plot, we see the opposite case, where the red circles and the green circles completely overlap. And that means that we've got no good option for our system to pick from, and so it fails as well. And this highlights why it's so important to pick different failure modes in your underlying configurations. And that brings us to our discussion. So, as a summary of the contributions in this thesis, in our first contribution, we used performance heuristics to detect individual target pose estimates with unacceptable errors and to characterize localization performance for specific camera viewpoints. We then went on to use these detections to improve localization accuracy through filtering and informing robot trajectories. In our second contribution, we combined performance heuristics with information about robot motion in order to predict localization failures ahead of time for specific trajectories. And in our third contribution, we used heuristic-based self-assessment to improve localization performance, this time by switching between different configurations specifically chosen for complementary performance. So there's three particular areas for potential future research that I'm quite excited about. In our experiments, we have simulated some aspects of surgery in our testing, so different robot trajectories and human anatomy models. However, there are a lot of conditions that we cannot replicate in the lab, and so I'd be really interested in collecting validation data sets from cadavers and using those to validate our approaches with more realistic data. Secondly, we've used one particular kind of 6 degree of freedom pose estimation system throughout our work, and I'd be interested to explore different underlying pose estimation systems. Some changes will probably translate quite easily, like using deep learned features instead of handcrafted key point features, but significant changes will also mean we'll need to investigate new performance heuristics that are suited to the particular approaches that we're using. And this last one's a little bit more blue sky, but I think it's a really cool thing. And that is improving generalization of localization forward prediction. So we've built a heuristic model for particular types of motion, but I'm really excited, and I think it's a really interesting opportunity to explore using implicit representations and volume rendering approaches to predict localization failures before they occur. I think that these methods will potentially allow us to build representations of the scene on the fly and then render camera viewpoints that we've never visited in order to assess whether localization at that place is possible. And that, I think, would be a really cool thing to explore. So that brings me to the end of my seminar. Thank you, everyone, for showing up. I'm really humbled that so many people came to hear me talk.